Hi, today we will be talking about Princeton365, a diverse dataset with accurate camera pose. We will be presenting Princeton365 in ICCV 2025. The problem of SLAM consists of taking in a monocular, stereo, or RGB video as input, and outputting camera poses for each frame, and a 3D reconstruction of the scene. SLAM methods are evaluated by comparing predicted camera poses to ground truth camera poses. However, a big issue with the current SLAM benchmarks is that they either lack data diversity, ground truth accuracy, or full 6-DoF camera motion. For instance, self-driving benchmarks generally cover a lot of space, but lack accuracy. They also lack 6-DoF motion, since the camera only moves on a 2D plane. On the other hand, accurate benchmarks are not diverse. For instance, motion capture-based benchmarks have millimeter accuracy, but they lack diversity, since it is difficult to set up a mocap rig in novel environments. Our benchmark Princeton365 bridges the gap between data diversity and ground truth accuracy. We record 365 sequences in total, with millimeter camera pose accuracy and full 6-DoF camera motion. Princeton365 has roughly 10 hours of recording and 2 million frames. Here are some example sequences from our benchmark. We capture scenes with challenging lighting conditions, non-Lambertian objects, and dynamic objects. Our approach consists of combining a 360-degree camera with calibration boards. When recording a sequence, we render two views. The ground truth view only sees the calibration boards and is used to obtain the camera poses, while the user view is provided to the method that will be evaluated, and it does not see the calibration boards. Here's a mock demonstration of how we collect data with our camera rig. It takes roughly 5 minutes to set up data collection in a novel environment. We propose a novel method to obtain ground truth camera poses from the calibration boards. At a high level, this method first initializes camera poses and board poses using perspective endpoint and pose graph optimization. It then jointly optimizes the camera poses and board poses with an algorithm that we call bundle PMP. Bundle PMP minimizes the reprojection error using the 2D and 3D correspondences.
We also propose a new evaluation metric that calculates the average optical flow magnitude induced by the estimated camera pose. Existing metrics, such as ATE, would consider a 10 cm error made when seeing a distant landscape to be the same as a 10 cm error made when seeing close-up objects. In contrast, our induced optical flow metric would penalize the latter more than the former. As a result, our new metric allows us to compare methods across scenes of different scales. To calculate the induced optical flow, we obtain depth distribution using a stereo camera. We mount the stereo camera on top of the 360 camera and use an NVIDIA Jetson to record. We use a laser pointer to sync the two cameras. We release the stereo output as well as the IMU output so that stereo inertial methods can be evaluated. To compute the induced optical flow, we sample a grid of pixels from the ground truth camera pose and reproject them to the estimated camera pose. We integrate the flow magnitudes over the depth distribution produced by the stereo camera. We externally validate the accuracy of our ground truth poses by comparing them to the output of a motion capture system. We also compare our ground truth poses to the poses obtained by Colmap. As we can see, our method achieves millimeter accuracy compared to Colmap that achieves centimeter accuracy. Our novel ground truth method allows us to propose a challenging NVS benchmark consisting of 6 sequences. This benchmark includes scenes with 360 scans around non-Lambertian setups due to the interest in the NVS community for such scenes. Current NVS benchmarks don't cover such scenes as they use Colmap to extract ground truth, and Colmap tends to fail on non-Lambertian scenes. We train NERF and Gaussian splatting methods on our NVS benchmark using poses from Princeton365 and Colmap. We report PSNR and LPIPS metrics on the validation views. While Colmap fails to output poses on 5 out of 6 scenes, our method always succeeds. We see that when Colmap does output poses, our method achieves higher rendering quality on validation views. We also evaluate state-of-the-art SLAM methods on Princeton365. Our benchmark is challenging even in simple cases. For example, here we saw a sequence that is a slow scan around a couple of objects. State-of-the-art methods such as DPVO and DPV-SLAM fail to recover camera poses for this scene since the entire view is covered by a non-Lambertian tarp. Thank you so much for your attention.